So we continue our studies on examples of motion on rough surfaces. We have already done a few examples on them, and let me recall them. We have first done the motion of a block on a horizontal floor. Then we compared the push versus pull, which one is more difficult on horizontal rough ground. We did the motion of a block down an accelerated vertical wall, and then we have done blocks supported on a steep inclined plane. So I'll be choosing more examples. I have intention of doing at least 2 more examples in this section, because you understand under real situations, frictional force is there, surfaces are rough, and we must learn to solve physics problems, taking into consideration the very real frictional forces which come into play. So our next topic, our next example of motion on rough surface will be a block supported on a rotating inclined plane. We shall consider a block on a steep inclined plane, and you'll see that if the plane rotates about an axis, how it might affect the block stability, and can we stop the block from sliding down the inclined plane. So since we'll be introducing a pseudo force in a non-inertial frame in this problem, it is a good idea that if we could recall a few words about pseudo forces and non-inertial frame at the beginning of this discussion. Suppose we have got a frame of reference here, and let me call that frame of reference as OXY, and this is attached to the ground. In that case, for observing terrestrial phenomena, we can consider this frame to be an inertial frame. I say inertial frame is one in which Newton's laws are valid. So here we have got a frame of reference OXY that is attached to the ground, and hence it is an inertial frame of reference. From this frame, let us observe a particle that I call P here, and expressed by this small dot as you can see on the screen. And when we consider the particle P from this frame, we know that we have to consider only real forces acting on the particle. There is no question of any pseudo forces. We identify the real forces, define of course x and y axis, and write equations of motion of the particle P. Now suppose under a set of real forces, this particle is describing a circular path. That let me show you here, that suppose the particle is moving in a circle as I show you on the screen. Now this is happening under a set of real forces, and you know that whenever a particle is exhibiting a circular motion, there is an acceleration of the particle towards the center of the circle. So if this is the center of the circle, as you can see by the small tiny dot, there must be an acceleration of the particle towards the center of the circle, and that we called centripetal acceleration, given by the symbol say AR, where R means radial, is directed towards center of the circle in the radially inward direction. You also recall the magnitude of AR is given by V square by R, where V is the speed of the particle at an instant, and R is the radius of the circle described by the particle. Now suppose I now want to introduce another frame of reference that is attached to the particle itself. So let's recall quickly what I said here. Here is a ground frame, inertial frame, and only real forces acting on the particle P. And under a set of real forces, let us assume the particle P is moving in a circular path and of radius r and speed v, so that there is an acceleration, centripetal acceleration AR, directed towards center of the circle. Now we attach another frame of reference, and we shall call it say O dash x dash y dash. So a new frame of reference attached to the revolving particle. So let me call that a revolving frame attached to the particle P. So you see that since we see this frame itself has an acceleration of AR towards center of the circle with respect to the ground frame, we conclude that this frame attached to the particle P must be a non-inertial frame of reference, because it's attached to a revolving particle P and has an acceleration. And in this non-inertial frame, if we want to investigate the particle P's motion, we have to consider not only the real forces, but also a pseudo force acting on the particle that's acting opposite in direction to the acceleration of the frame. So while we observe and investigate the motion of the particle P in a frame attached to itself and the particle is in revolution, we must consider the real forces and a pseudo force, and you know that the pseudo force, let me use the symbol Fp for that, and vectorially Fp is given by simply minus mass of the particle into the acceleration of the frame from which the particle is observed, and that frame is of course attached to the particle itself. So here you see the case of two different frames. In the ground frame, particle has got only real forces acting on that, but from a frame which revolves along with the particle has got real forces acting on it as well as a pseudo force given by minus MAR, which means direction of the pseudo force is opposite to the acceleration of the particle, and its magnitude is given by the product of mass and the acceleration of the frame from which the particle is being observed. Keep this in mind. We shall meet that very shortly now as we discuss the block supported on a rotating inclined plane. Let us now have a look at the situation of the problem that we investigate now, and we keep this side by side with my initial figure for a quick comparison. Here is a steep inclined plane, a rough one, and the inclination of this rough inclined face is more than the angle of repose between the inclined plane and a block that is placed onto this inclined plane, right? So here is a block inclined plane system, and normally if there is no other force and the situation like that, the block would come down, slide down the inclined plane, because the inclination, as I said, this angle theta is greater than the angle of repose theta s between the block and the inclined plane. Theta s depends only on the value of mu s between the block and the inclined plane. You know that already, and I have taken a steeper plane than that. This theta is more than theta s. So normally the block would have come down this inclined plane. And is there any way to hold the block here, letting it not move, keeping it at rest? We already have seen in a previous example that if we could apply a force onto the block in an inclined manner, then within a range the force can keep this block at rest. But now we shall consider another possibility where suppose this inclined plane is made to rotate about an axis of rotation that you can see here, and this inclined plane rotates about this vertical axis. So as the plane rotates about this axis, as you can see, the block will be moving in a circular path, and let me show you this circle. This is a circle in which the block is moving, and as you can see, I treat this block as a particle, so my circle passes to the center of this block, and let's assume that this circle has got a radius of r, as I'm showing here. So here the block revolves in a circular path of radius r with a linear speed of v, as I have shown in the figure. Comparison between the previous case on the left side figure and the right side figure here, since the block is moving in a circle, it will also experience an acceleration it has got, and the acceleration is AR, the centripetal acceleration, as you know, which is numerically given by v square by r. And so in a frame attached to this block, the block experiences not only the real forces but also a pseudo force that is acting to the right in my figure. So here we have got a pseudo force acting on the block, which is given by minus m into air. Remember, this force is experienced only in a frame attached to the block itself. So let us now see how this pseudo force can prevent the block from sliding down. Looking at the figure carefully, you can see a component of the pseudo force is acting parallel to the inclined plane up the incline. So since pseudo force is given by m into AR, and again AR is v square by r, which means the magnitude of pseudo force is given by simply m into v square by r. So you see that if the value of v is too small, in that case the component of pseudo force is also small and the block will come down. It cannot be stopped. On the other hand, if the value of v is too large, in that case the component of the pseudo force will be so large the block will start sliding up the incline. So the two possibilities, there has to be a lower limit below which the block slides down, and there's an upper limit for v above which the block slides up the incline. And our job is to find out the range of this value of v, the linear speed of the block's block in circular motion, that we shall be doing in details.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.